Okay, so let's take a minute and talk exactly about what a p-value is, statistically significant, and the conclusion should look like when we're doing tests of significance. All right, now that you know our hypothesis, how to write one, and what your p-value is, this is how you're going to write a conclusion in context in order to state our findings, okay? Now, this template is here. There's also a template on Blackboard that you can print out in order to look at it, but this is how you should write your conclusions every single solitary time. So your first sentence is going to say, first of all, we have sufficient or insufficient evidence to show that the alternative hypothesis is true or false. Or we have sufficient or insufficient evidence to reject the null or fail to reject the null. There is sufficient evidence to show that the alternative hypothesis is 50 pounds, whatever you're testing in context, okay? And then this right here, this second sentence, this is the interpretation of the p-value, okay? Now, because remember, what we're doing is we're taking a look at the true mean or proportion, that's our hypothesis, and we're testing how far away our sample is from that. So if the true mean or proportion of a variable is really 80 or whatever value stated in the null, then the probability of observing a statistic as extreme or more extreme as ours is the p-value. So basically you're giving what the p-value means. So we're stating we're looking at the curve based on the mean or proportion of the value stated in the null and giving the probability of observing the statistic that we collected to test the null alternative. Okay, this is unlikely or likely to have happened by chance alone. It's likely to have happened by chance alone if the p-value is high and you're failing to reject the null. It's unlikely to have happened by chance alone if you're rejecting the null, and that's saying that, hey, our statistic was really far away from what the true value should be, so we really think that that true value is incorrect. Okay, you could also say this is statistically significant or statistically insignificant at the alpha equals 0.05, 0.1, whatever level. All right, so what are some common errors that students do when they're writing their conclusions? Number one is they don't put the conclusion in context. Somewhere in that conclusion, you must put it in context, okay? Number two, don't ever state that you're accepting the null hypothesis, because our test is never to say we know the null is true, okay? We're just testing to see how much evidence we have against the null. So we always fail to reject the null. All right, so for example, it would be incorrect to conclude that job satisfaction is the same for machine-paced and self-paced. All right, so that's saying it is the same. We're not saying that it is. That's basically saying the null is true. We're just saying we don't have any evidence to reject it. If we fail to reject, we're saying that the other value is one of the plausible values for the parameter. So that's basically saying, okay, so we have this curve. We're assuming that the null value is true, is 80% or whatever. If we fail to reject the null, we're saying basically, okay, think about it in terms of a confidence interval. We're saying that the statistic that we got is actually a plausible value that could be the parameter. We're failing to reject the null, so we can't say that it's something different than what the null actually could be. So just be careful with that wording. Make sure you link the conclusion to the p-value. All right, how do you do that? You're rejecting or failing to reject the null if the p-value is too large or too small. So you want to make that connection. And I often say, like, I fail to reject the null because p is less than alpha. Or p is greater than alpha. I reject the null because p is less than alpha. So that's making that connection between the two. Okay, so let's just take a look at some examples and writing a conclusion. So a company has developed new deluxe AAA batteries that's supposed to last longer than the regular AAA battery. However, these new batteries are more expensive to produce, so the company would like to be convinced that they really do last longer. Based on years of experience, the company knows that its regular AAA batteries last for 30 hours of continuous use on average. The company selects an SRS of 15 new batteries and uses them continuously until they are completely drained. Here's your significance test. So the null is that the mean's equal to 30 hours. That's based on their previous experience. Our alternative is saying, okay, we actually think that the mean is now longer than 30 hours. Notice how we've defined what mu is. Mu is the true mean lifetime of the new deluxe AAA batteries. We get a p-value of 0.0276. We want to know what conclusion can we make at the alpha is 0.05 and what conclusion can we make at the alpha is 0.01. All right, so let's take a look at our two conclusions. Now, first of all, if we take a look at this alpha as 0.05, the 0.0276 is less than that alpha value. And I just want to show you quickly where that came from. Okay, so this is your curve. Okay, think of your alpha is 5% of the curve. That's this area up here. This is all the areas where you're rejecting the null, and this area inside here is where you're failing to reject the null. So basically what that's saying is this is all of the plausible values of the statistics that could be if the mean was 30 hours. Those are plausible values for the parameter. But out here, once we're this far extreme, those are not plausible values. So if you take a look at this probability, 0.0276, if I start on the left-hand side of the curve, 0.2076, that's going to end up, this is 5% of the curve, this is only 2% of the curve, so that's in this rejection region and hasn't quite hit in the 95% of the region where we're failing to rejecting the null. So the conclusion, based on the previous slide, since the p-value, 0.0276, is less than alpha, that's connecting your p-value to your alpha, the sample result is statistically significant, okay, and we know specifically what that means in statistics. We have sufficient evidence to reject the null and conclude that the company's deluxe batteries last longer than 30 hours on average. So notice how you're saying reject the null, and then you're giving the answer in context. Now, what about at the 0.01 level? Okay, now the 0.01 level is going to be over here. Okay, so if we're going to do this, okay, this is going to be 0.01. It's a really light color of yellow. Okay, so the 0.01 is saying this is only 1% of the time am I rejecting the null. 99% of the time I'm going to fail to reject the null because it's within a plausible area of where the parameter should be. So since the p-value is greater than alpha, so if we're talking about areas of the curve, it takes up that 0.01 plus a little bit more of that. So it's gone into the rejection and then into the region where I failed to reject. The sample result is not statistically significant. We do not have enough evidence to reject the null in this case. Therefore, we cannot conclude that the deluxe AAA batteries last longer than 30 hours on average. Okay, now, this is just taking a look at sort of where the rejecting and failing to rejection region comes from. So this is what I was explaining on the other side. So at alpha is 0.05, that's the dividing line between failing to reject the null and rejecting the null. So failing to reject the null 95% of the time, rejecting the null 5% of the time. Basically, what this is saying is there's 5% of the area you're rejecting, 95% of the area where you're failing to reject. If P is greater than alpha, then the area shaded under the curve takes up all the 5% region and a portion of the fail to reject region. Therefore, we fail to reject the null. And always, if the rejection region is below, okay, and that's 5% below, start with that side and you're going to say, okay, if I'm going to color in 7% of the curve, first I'm going to color in this 5% and then this 2% over here. If it's above, you're going to say, oh, I'm going to color in this 5% and then this 2% over here, so I'm failing to reject the null. Okay, if P is less than alpha, then the area shaded under the curve only takes up a portion in the rejection region and we fail to reject the null. So if this is 5% and our p-value is 2%, I'm only shading in 2% of the curve. I'm just in the rejecting the null region. All right, so let's just take a look at this example. What I would like everybody to do is just take a minute and read it. Okay, we're going to put it all together and we are going to answer this question: how can we use everything we have learned to answer the question of, consider that a different sample of tasters would have resulted in different scores and that some of the variation is expected due to chance. Okay, actually I lied. I'm going to sort of go through this one because this is kind of a new example. Okay. So diet colas use artificial sweeteners to avoid sugar. Colas with artificial sweeteners gradually lose sweetness over time. Manufacturers therefore test colas for loss of sweetness before marketing them. Trained testers sip the cola along with the drinks of standard sweetness scores and on the cola and give a sweetness score of 1 to 10. The cola is then stored for a period of time and each taster scores the stored cola. This is a matched pairs experiment. The reason it's a matched pairs, remember, is because what you're doing here is you have a cola, you taste it, give it a sweetness score of 1 to 10, say we give it a sweetness score of 8, put it in a refrigerator, we taste the same exact cola after a certain amount of time and give it another sweetness score, say, 8 or whatever. So it's matched pairs because I'm tasting the same cola twice and I'm giving it 2 different scores. The bigger the difference, the bigger the loss in sweetness. Okay, so this is the difference in the taste tester score. So what that means is they subtracted them. So if they did like 8 and then went to 5, or sorry, 8 and then went to 6, it would have a difference of a sweetness score of 2. So this was the answer to the subtraction problem from the before minus the after. Okay, the sample mean X bar indicates a small loss of sweetness. So that X bar is telling us that it lost 1 sweetness score since those were the difference. Consider that a different sample of tasters would have resulted in different scores, and at some point, and there's some variation in expected due to chance. So the question is basically like, what is the true mean of the loss of sweetness in the cola? Okay, so let's do a test of significance in order to answer that question. Number 1, what you're going to do is identify the parameter. The parameter of interest is mu or p. So we're either looking at a mean or proportion. This is basically what we did in the last section. We're just stating, okay, what are we trying to find? Is the true mean difference in sweetness loss 1? Okay, we're going to state the null and alternative. Okay, so remember the null is there's no effect or change. This is what we're trying to find evidence against. The alternative is there is some effect or change, and you're going to want to read the question to figure out how you're going to answer this. You're going to calculate a statistic to estimate the parameter. So basically what you're going to do is you're going to find the z-score of your statistic and see how far away it is from that mean that we think is true. If it is far away, we're going to reject the null. If it's not, fail to reject the null. So that's finding your z-score and then your p-value. You're going to then calculate the p-value and make a conclusion using the template that you provided. We're going to get into this more in section 8.2, but I wanted to give you a heads up of what we would be doing. Okay, so we're not going to be doing this right now, but that's what we're going to do to answer that question on the previous page. All right, now you do a test of significance, you draw a conclusion. However, it doesn't necessarily mean your conclusion is correct. We're human, we all make mistakes, okay? Sometimes your conclusion could be wrong. There are 2 types of mistakes we can make, okay? Now, one mistake is we reject the null when the null is in fact true. Okay, now in statistics, we're going to give that a specific name. That's called a type 1 error. So we say, hey, we think the null is false, but it actually is true. Okay, we shouldn't have rejected it. A type 2 error is we fail to reject the null when the alternative is true. So type 1 is we get rid of the null when the null is true. Type 2 is we fail to reject the null when the alternative is true, and that's committing a type 2 error, okay? And I'll go through an easier way to remember both of these. All right, so let's just look at a table and see what when we have a correct conclusion or an incorrect conclusion. So this is the truth of the population. This is saying the null is true, the null is false, and we don't ever say the alternative is true, but just that's what I'm sort of using here, okay? So if the null is true, if the null is in fact true and we reject the null, that's a type 1 error, okay? Because the null is true and we've said, hey, let's get rid of it. We've made an error in something in our calculations, or we just did something wrong. If the null is true and we fail to reject the null, we've made a correct conclusion. So the null is true and we've kept it, we're good to go. What happens if the null is actually false? If the null is false and we reject it, hey, we have a correct conclusion, we're good to go. If the null is actually false, but we fail to reject it, that's a type 2 error. So I think of a type 2 error as type 2, 2 lines, double Fs. The null is false and we fail to reject it. Okay, now the most important thing when we're doing this is to make sure that we understand this in context. So we're going to look at a specific case later, but think of a type 1 and type 2 errors as a trial. When someone goes to trial, the jury's conclusion could be wrong, but first let's define a null and alternative hypothesis to see what this looks like. When you go to court, you're always going to assume that the person is innocent. You're innocent until proven guilty. The alternative is that they are not innocent or they're guilty. What would a type 1 error be? A type 1 error would be that the jury could convict an innocent person. So in a trial, you're assuming innocence until proven guilty. If the null is true, they are innocent, but the jury rejects the null and states that they're guilty, a type 1 error has been committed.